everyone, I am Ms. Hu, your physics teacher. In this video, we'll be going through the turning effect of forces. So we'll be learning about making memorable moments. Alright, not those kind of moments. We'll be learning about moments in terms of physics. So what we'll be covering in this video lesson are how to use the formula of moment equals force times perpendicular distance. We'll also learn to state and define the principle of moments, as well as how to state and identify the conditions of equilibrium. So first of all, what are moments? Now, in physics, moment is quite simply the turning effect of a force. So if you were to apply a force on an object or a system, and we find that it causes a rotation or a turning effect, that's moment. So a classic example of a moment in action is a seesaw. So if you have someone sitting on either ends of the seesaw, you have one point, which is the point of pivot. You find that as we apply force, the system or the seesaw will rotate or turn. Now remember that in physics, we like to measure and quantify everything. So moment is the physical quantity which quantifies the turning effect of a force applied on a system. So in this seesaw, we have a pivot point, which is a point of rotation. And when we apply a force on either side, we find that the seesaw will rotate. So moment is the quantification of that turning effect of the force. So how do we calculate moments? So moment is calculated as force times perpendicular distance between force and pivot. And in fact, the definition of moment is based on this formula. So if you are asked to define moment, moment is the product of force and perpendicular distance between the force and pivot. Here's a little lame joke / meme for you. My students know that my lessons are not complete without a meme or a lame joke. I haven't really included a meme or a lame joke in all my videos because I know some jokes are dated, but I decided to include one now anyway. Before we look at an example, let's just quickly look at the unit for moment. So to determine the unit of moment, we just need to use the units in this equation. The SI unit of force is Newton. I'm going to write that over here, Newton. While perpendicular distance is the same as distance. SI unit for distance is meters. So when you look at this equation, you'll find that the unit for moment is Newton times meter, giving us Newton meter. Now, next I'm going to explain a little bit about the perpendicular distance between force and pivot and what that means. So on this slide, let's look at a couple of examples. On the top diagram, we have a plank balanced on a pivot. So the yellow triangle here is the pivot. And when we apply a force on the left side, we'll find that this would cause a turning effect that is anti-clockwise. So this force will produce an anti-clockwise moment. The distance that we're talking about is between the pivot and the force. So I'm going to draw the distance out here. What it means by perpendicular distance is that the way we measure distance is perpendicular to the direction of the force. So you can see the force is going downwards and the distance is measured horizontally. So the moment calculated in this case is force times distance as shown. Now, if the force was on the right hand side instead, this would cause a clockwise moment, and the distance measured is also between the pivot and the force. Again, similarly, the way the distance is measured must be perpendicular to the direction of the force. So just to explain the difference between these two, the way we calculate moments are the same. It's just that the effect would be different. So on the top diagram, the moment will be anti-clockwise. So I'm going to write here anti-clockwise. It's alright to say counterclockwise. They both mean the same thing. Whereas the diagram on the bottom here would give us a clockwise moment. Now you may or may not be required to state the direction of the moment's rotation. If you're just calculating moment, you can just put F times D. However, the direction of anti-clockwise and clockwise will come up later in principle of moments. Before we go into that, let's look at another example where this time our plank or our system is not horizontal nor vertical. You'll find that it's at an angle this time. So how do we calculate the moment for the force being applied in this case? Now remember that the distance must be perpendicular to the direction of the force. So if you were to do this, where you take the distance from the force to the pivot like so, this is not correct. As you can see, the direction of the force and the direction where the distance is being measured are not perpendicular. So this measurement would be incorrect. So how do we get the correct value of the distance? So for students who are not sure how to get the distance, this is my suggestion. What you do is find the pivot point and draw a dotted line through that pivot point that is parallel to the force. So you can see that the force is acting downwards. We're just drawing a blue arrow here just to emphasize this. So the force is acting downwards or vertical. So we're going to draw a dotted vertical line through the pivot like so. The distance that we would measure is between the force and this dotted line where the pivot is. And we got to make sure that the distance measured is perpendicular to the direction of the force like this. So this is how we get the perpendicular distance between the force and the pivot. The way we measure the distance must be perpendicular to the direction of the force. As you can see, the pivot is on this side. When you apply the force to the left side of the pivot, this will cause the system to rotate anti-clockwise. So just to emphasize the direction here, I'm going to write anti-clockwise moment on the left hand side. Let's take a look at another example. Let's say now in this case the force is applied to the right under the plank like this. How do we get the distance? Now a lot of students are so used to thinking of forces being applied vertically that they always assume that the distance must be horizontal. So if you were to do this, where you take the distance from here to here, this is incorrect. Because as you can see, the force is also horizontal. Now the distance is parallel to the force direction. This is not correct. So how do we get the distance then? So let's use the guideline I suggested earlier. Find a pivot point and draw a dotted line parallel to the direction of the force. So in this example, the force is acting to the right. So it's actually horizontal. Let's draw a dotted line that is parallel to this force through the pivot point. So because the force line is horizontal, we'll draw a dotted line that is horizontal through the pivot. So the distance is measured between the force and this dotted line. Okay, that's not quite perpendicular. Let's try that again. So this is the correct distance. You can see how we measure the distance is perpendicular to the force, like so. So now the moment is force times this distance. In terms of the direction of the moment rotation, you can see the pivot is here. The force is pushing the plank to this side, causing a clockwise rotation. So this would be a clockwise moment. So even if you get systems which are angled like this, you always need to find the distance that is perpendicular to the direction of the force applied. So remember the suggested guidelines. Draw a dotted line through the pivot point that is parallel to the force, and we take the distance between the dotted line and the force. So that's how you calculate the individual moments. Let's now learn about the principle of moments. The principle of moments states that when a body is balanced, the total clockwise moments about a point equals the total anti-clockwise moments about the same point. What that means is that whichever point that we were to observe on a system, the total clockwise moment will be equal to the total anti-clockwise moment. For now, you can think of it as the point is the pivot point, and the total clockwise moment about that pivot point is equal to the total anti-clockwise moment about that same pivot point. In other words, you can think of this as the net moment is equal to 0. So that means that there is no net moment, therefore no net rotation. Does that mean there are no moments acting on the system? No, there are moments acting on the system. It's just that the moments cancel each other out, creating no net moment or zero net moment, and therefore no rotation. So let's look at some general examples. In this situation, we have a pivot in the middle and we have two forces, one acting on either side of the pivot. So as you can see, F1 is on the left hand side and F1 is acting downwards. So if F1 were to act on the system, this would cause an anti-clockwise moment. So what I'm doing here is I'm just indicating the direction of the rotation, and I'll write here ACW, which means anti-clockwise. So this creates an anti-clockwise moment around the pivot. So the anti-clockwise moment is calculated as F1 times the distance between F1 and this pivot, which I will label as D1. Now on the right side, we have F2 pressing down, and when F2 acts on the system, it creates a clockwise moment. So I'm labeling this rotation as CW to indicate clockwise moment. So the clockwise moment, I'm just writing CW for short, clockwise. Clockwise moment is calculated as F2 multiplied with the distance between the pivot and F2, which I'll label here as D2. So you can see that in this system, there are moments acting on the plank balanced on the pivot. There's an anti-clockwise moment as well as a clockwise moment. If there is no overall rotation, that means there's zero net moment, meaning principle of moments apply in this case, the anti-clockwise moment is equal to the clockwise moment. Which means that the overall calculation is F1 times D1 equals to F2 times D2. And that's how we can apply principle of moments in this example. Now, a very common mistake that a lot of students make is that they think that, oh, the left side moment will be equal to the right side moment. That is not true in all cases. That only is true in a situation like this, where it so happens that the left side moment will create only anti-clockwise moment and the right side moment will only create clockwise moment. But you can get situations where the moments on the left side don't equal to the right side. So never assume left side moment equals the right side moment. It's always anti-clockwise moment equal to clockwise moment. For example, if we get a situation like this, where now we have three forces and the forces are acting in different directions. We've got two pressing down and one pressing up. So let's look at each individual force and the direction of moments that they will create. So for F1 presses down, this will create an anti-clockwise moment around the pivot. So I'm just drawing a little arrow here to show that this is going anti-clockwise. Before we start calculating the anti-clockwise and clockwise moment, let's look at all the forces first in the direction of the rotation of the moment. So for F2, when it presses down, it will create a clockwise moment. Now let's see. F3 is on the right side, but it's pressing upwards. When determining the direction of rotation of the moment, ignore all the other forces first and just focus on that singular force. So for F3, pivot is on the side. When F3 presses up, you'll find that F3 will create an anti-clockwise moment. So in this example, we have two anti-clockwise moments and only one clockwise moment. So that's why you cannot say, oh, left side moment equal to right side moment. You can't, because as you can see in this example, on the right side, we have one anti-clockwise and one clockwise moment. So if this system was balanced, the anti-clockwise moments equal to the clockwise moment. So to solve this question, we'll have to take the sum of the anti-clockwise moment over here as total. The total anti-clockwise moment must equal the total clockwise moment. There are two anti-clockwise moments here, and how we calculate it is like this. So the distance between the pivot and F1, I'm going to label here as D1. The distance between F2 and the pivot I will label here as D2. Let me just fix this a little bit. And the distance between F3 and the pivot I'll label here as D3. So remember that moment is just force times distance. So the anti-clockwise moment are caused by F1 and F3. So to total this, you just take F1 times D1 plus F3 times D3. So that's a total anti-clockwise moment. Clockwise moment, there's only one, which is F2. So we'll take it as F2 times D2. And of course, to solve this, just substitute the values that you can get from the question in here and you can solve the problem. So now, I hope you're getting the hang of it. Let's look at another example. So now in this case, we've got 3 forces acting on the left side and 1 force acting on the right side. So to solve this, remember, it's not left moment equals to right moment. It's anti-clockwise moment equals to clockwise moment. So whenever you're not sure which is anti-clockwise and clockwise, always determine and write down which ones are causing anti-clockwise and which ones are causing clockwise rotation. So look for the pivot. A pivot's in the middle. F1 will cause an anti-clockwise moment. F2 will also cause an anti-clockwise moment, whereas F3 will cause a clockwise moment. F4 will cause anti-clockwise as well, which means that in this situation, although there are 4 forces, it's not 2 of clockwise to anti-clockwise. There are 3 anti-clockwise moments and 1 clockwise moment only. The distance is always taken between the pivot and the respective forces. So to save time, I'm just going to draw them all in the same color. So we've got D1, D2, D3, and D4. So the total anti-clockwise moment is equal to the total clockwise moment if this system is balanced. That means principle of moments apply in this case. So total anti-clockwise moment, there are 3 anti-clockwise moments, so sum them all up. F1 times D1 plus F2 times D2 plus F4 times D4. There's only 1 clockwise moment caused by F3, so this is F3 times D3. That's how you solve this example. So just substitute the values that you can get from the question and solve it from there. So now I hope you're getting the hang of this. Remember, the total anti-clockwise moment must equal to the total clockwise moment. Now, in comparison, this question must look so much simpler. So what's the deal over here? Now I want you to imagine in real life, is it possible for us to balance the system this way? Yes, correct? Now, if you look at the difference between this example and the others, you'll find that the pivot is no longer in the middle. It's off to the center. And if you didn't have a force here, and you tried to balance an object with the pivot right at the edge, let me try to match the diagram here, of course it's going to fall. Why does it fall? Why does it rotate? Why is there a moment? Because there is the weight of the object causing the moment. In the earlier examples, the pivots were all in the middle, and we didn't take into account the weight in that case because the weight is directly on the pivot. So the distance between the weight and the pivot is 0. So therefore, there's no moment. But in this case, the weight is not supported by the pivot. So the weight will now cause a moment around the pivot. So that means in this situation, the force can balance the moment caused by the weight. As you can see, the weight will cause a clockwise moment, while the force F will cause an anti-clockwise moment. So the distance here, I'm going to label this as D1, and the distance between the weight and the pivot, I'm going to label here as D2. So the total anti-clockwise moment is equal to the total clockwise moment. So this example seems a lot easier compared to the others, and the reason why I'm mentioning this is because some students forget that there is weight of the object. So never assume that the pivot is always in the middle. You got to look at the question, and if the pivot is off to the side, you must always measure the distance from that pivot point. And if the uniform object has the pivot off to the side, then you must take into account the weight of the object acting on the system. So now let's take a look at this example. As you can see, the pivot is now off to the side. F1 will create an anti-clockwise moment, and say the distance here is d1. F2 will create a clockwise moment, and the distance here is d2. Now, a common mistake that a lot of students make is that they equate this anti-clockwise moment of F1 times d1 straight away equal to F2 times d2, and then try to solve it from there. Now, that's not correct, because as we just looked at the example before this, there's also weight of the plank. So if this was a uniform plank, this is the weight, this is the distance. You must take into account the moment caused by the weight. And you can see that this weight creates a clockwise moment. So sometimes the question may mention the weight, sometimes they don't. But if they don't, then you must remember to add the weight in, especially if the pivot is off to the side. So don't get fooled, don't get tricked. So now we know total anti-clockwise moment equals to total clockwise moment. So you have, for the anti-clockwise moment, only F1, so this is F1 times d1. Whereas for the clockwise moment, we have F2 times d2 plus the weight times d3. And then sub in from here and solve the question. Now, what if you get a question like this? So this example is a combination of the earlier two examples, example 2 and 3, of the forces acting on a plank that is placed at an angle. Now, let's say the pivot is placed in the middle of this uniform plank, so we can ignore the weight for now. As you can see, both forces are acting on the left side of the pivot. F1 is pressing down, creating an anti-clockwise moment, while F2 is pushing to the right, creating a clockwise moment. So if the system was balanced, that means the anti-clockwise moment would be equal to the clockwise moment. Let me just remove this word, and then let's recall to get the distance. So for F1, it is between F1 and this vertical dotted line. That's how we get the distance. Whereas for F2, because it's acting horizontally, the distance is measured between this horizontal line and the force, which I'll label as V2. So if the system was balanced based on the principle of moments, the total anti-clockwise moment would be equal to the total clockwise moment. The anti-clockwise moment is caused by F1, so we have F1 times D1, and the clockwise moment is caused by F2, so it will be F2 times D2. But what if the pivot is not in the middle, like this? So when you see this, you must remember that the weight of the object is also going to cause a moment. So before we even find anti-clockwise and clockwise, just to remind yourself, oh, there's weight. Let's draw the weight line from the middle of this system downwards, and this is weight. Now let's find which one creates an anti-clockwise and clockwise moment. So you can see that F1 is going to cause a clockwise rotation around the pivot. So I'm going to label here CW. F2 is also going to cause a clockwise moment. F3 is also going to create a clockwise moment. Only W is going to create an anti-clockwise moment. So the distances are measured based on the direction of the forces. So F1 is vertical, therefore we would take F1 from here to here. So this would be D1. F3 is also vertical, so this would be D3 for F3. The weight line is also vertical, so this is I'm going to label this as D4 because F2 is over here. This would be D2. So based on this diagram, the total anti-clockwise moment would be equal to the total clockwise moment. For the anti-clockwise moment, there's only the moment caused by the weight. So I'm going to write here W times D4. The total clockwise moment, there are 3. So it's F1 times D1 plus F2 times D2 plus F3 times D3. So that's how you'd solve example 10. Now, are there other kinds of examples? Of course. But I hope that all these different examples have given you an idea now on how to solve various kind of questions. So regardless of whatever the angles are, remember that the moment is always calculated as force times the perpendicular distance between the force and the pivot. And if there's no rotation, remember that net moment is 0. So the total anti-clockwise moment must equal the total clockwise moment. And now let's look at the concept of equilibrium. So when something is in equilibrium, that means there is no motion nor any rotation. For this to happen, there must be two conditions. First of all, the net moment is 0, which means that the total clockwise moment is equal to the total anti-clockwise moment where the principle of moments apply. Secondly, the net force must be 0, which is the concept of balanced forces, also known as forces in equilibrium. So remember, this situation is when there's no rotation and no motion. So if you have a question where they told you that the system is in equilibrium, you must know of these two conditions. So for example, if you have a situation like this, where this system is in equilibrium, that means that the net moment is 0 and the net forces are 0. Now, if you have a system where there are two pivots, how do you solve the question in this case? If you are required to calculate the moment, remember that you always calculate the moment around one pivot at a time. So for example, you calculate the total moment around the left pivot only, or you take the moment around the right pivot only. What you must know is this: what are the forces acting on the system? So you have F1 and F2 pressing down, and as we saw in the earlier examples, there's also weight. So if this plank was uniform, that means the weight is acting from the middle. Now, does it only have downward forces? No. You must remember that when you have an object resting on two supports, these supports would also push back up with a reaction force, which I'll label here as R1 and R2. So R1 and R2 are the reaction forces acting upon the system by the support. So if you were required to calculate the moments, you calculate the moment around one pivot at a time only. So say for example, we want to calculate around this point which I've marked here in red. That means you can ignore R1 because the distance between R1 and the pivot is 0. So R1 does not create any moments. So if we're looking at the moments about R1, you can see that F1 would create an anti-clockwise moment, W would create a clockwise moment, R2, yes, and R2 also must be considered in terms of the moment because it is a force. R2 can create an anti-clockwise moment, while F2 creates a clockwise moment. So you would measure the distance from the red point. So this would be D1. We'll take this as D2, this as D3, and this as D4. So total anti-clockwise moment is equal to the total clockwise moment around the red point. So the anti-clockwise moment would be F1 times D1 plus R2 times D3, whereas the clockwise moment would be F2 times D2 plus W times D4. And then you solve it from there. If you had to calculate the moments around the point where R2X, which is the purple point, you have to look at the respective forces acting around that point as well. So F1 is also going to create an anti-clockwise moment. F2 will also create a clockwise moment, but for W this time it's going to go anti-clockwise around the purple point. R1 will be going clockwise. So the total anti-clockwise moment, which is equal to the total clockwise moment around the purple point. So I'm going to label with different values of D because we already have D1, D2, D3, and D4. So for F1, I'm just going to draw it over here. I'm going to label it on top here. I know it's a little bit messy now, but I hope you can understand what's going on. Let's label this as D5. And let's say this is D6. Let's label this as D7. And between the red and the purple point, let's put this as D8. So we have F1 times D5 plus, the other anti-clockwise is the weight, so that's W times D7, and the clockwise moments are R1 times D8 plus F2 times D6. So if you have two or more pivots, remember you only take the moments around one pivot at a time. Now this is only principle of moments in effect. How does the balance force apply in this case? So if this system is in equilibrium, that means that the net force is zero. As you can see, all the forces here are parallel to each other, either upwards or downwards. So the total upward force equals to the total downward force. So I'm squashing it over here because yes, I took a little bit too much space with the calculation of the moments, but I hope you can understand. So the downward forces are F1, the weight W, as well as F2, while the upward forces are the reaction force of R1 and R2. So depending on what you need to solve in the question, you can use these equations and solve the values that you need to calculate from there. Okay, so this is a little bit complicated. Are there simpler questions? Yes, they are. So let's say you have a very simple question like this, where we have a plank that is supported by a cable on the right side and it's pressing on the hinge that's against the wall. So let's say in this case we have the weight of the plank pulling down, supported by the tension of the cable pulling up. If the hinge is the pivot point in this case, that means that the weight is going to create a clockwise moment around the hinge, while the tension in the cable will create an anti-clockwise moment. So let's say the distance here is D1 and this distance is D2. So to calculate the moments, we'll calculate the moment around the hinge. That means the total anti-clockwise moment equals to the total clockwise moment. This would give us T times D2 equals to W times D1. Now let's say the question tells us that the hinge creates an upward force, which I'll label as R. So if the system is in equilibrium, that means the forces are balanced. This would tell us that the upward forces equal to the downward forces. So R plus T equals to W. What if the cable was not acting upwards and you have a situation like this where the cable is at an angle? So assuming that this point, which I'm marking in purple here, is the pivot point, you'd solve it pretty much the same way as well. So we have the weight of the plank pulling downwards, and this time the tension in the cable is not acting upwards, it's acting at an angle. So to solve the moment about the purple point, which is the pivot, we have to be careful in this case because the distance is not so straightforward. So the weight will create a clockwise moment, while tension will create an anti-clockwise moment. The distance between the weight and the pivot point, I'm going to label here as D1. However, for the cable, you got to get the perpendicular distance, which means that you have to draw a line that's perpendicular to the tension line up to the pivot point. So this is D2, where this is perpendicular. So how do you get the value of D2? You'd have to use trigonometry. So depending on what values you are given here, let's say, for example, in this case, the angle of theta was provided. You will need to know the entire length of this plank, which I'm going to label here as L. And you can see we've got a triangle here where L is the hypotenuse and D2 is opposite to theta. So to get the value of D2 based on the angle of theta, you can see that sine theta equals to D2 divided by L, which means that D2 is L sine theta. If the weight is in the middle, that means that L is double of D1. So you can put this as 2D1 sine theta. Now, of course, it depends on whether the question gave you the value of L or D1. So you either use L sine theta or you can use 2D1 sine theta, depending on what values you are given in the question. So that's how you get D2. So to calculate the moments, you pretty much do the same thing as what we've been doing all this while. So based on the principle of moments, we calculate the moments around the purple point, where the total anti-clockwise moment is equal to the total clockwise moment. So the anti-clockwise moment is calculated as T times D2, while the clockwise moment is calculated as W times D1. Whereas for the net forces, in this case, the net force is 0, but you can't say upward force equal to downward force now because tension is acting at an angle. So assuming that at this point, it creates a normal reaction which acts perpendicular to the surface of the wall, like this. I'm going to label this as R. To solve the net force, you would have to draw the triangle and solve the forces in equilibrium based on the triangle. So you have W going down, R is to the right, and tension is acting at an angle where this is theta. And you use this triangle to solve the question depending on what you require to calculate. If you would like to see some worked examples where the question actually have numbers, or you want to see how to solve past year questions using principle of moments or the concept of equilibrium, I will share a separate video using those worked examples. For now, that's the end of this video. So I hope you found this video to be educational and helpful. Please subscribe for more free physics lessons. Do check out my YouTube channel for videos on other topics which you might find helpful. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page, that's ko-fi.com/physicsrocks. If you would like notes, quizzes, and syllabus updates, do check out my website at physicsrocks.com. Happy study!